Hey guys, this is example 3 for section 7.3. All right, so before I start, I'm going to tell you a joke, okay, that one of my daughters told me a few days ago. Why did the girl throw the butter out of the window? Why did the girl throw the butter out of the window? Because she wanted to see a butterfly. Get it? Because she wanted to see a butterfly, but it's butter and fly put together. There is your toddler joke for today. Ha ha ha. Example 3. Solve each. Give a general formula for all solutions. So I want to highlight this word right here. All solutions. List 6 solutions, okay? So first you're going to give me a formula for all of them, and then you're going to list 6 of them. So solve, you're going to do it old school, okay? So first I'm going to add radical 3 to both sides. The formatting of this looks a little bit weird. Hopefully it's better on your paper, on your notes packet, but I highly doubt it. Sorry about that. Okay. So 2 cosine of theta equals rad 3. Divide both sides by 2. So I'm going to move it here. So since the formatting, it's a little bit off. Cosine of theta is now positive rad 3 all over 2. Because this is a regular trig function, it has no restriction. That's why I can get all of the formula. And there are unlimited number of solutions. So let me just bring you back to this right here. See these right here, A, B, C, D, E, F? Notice how if I don't limit this here in a very first example, then there is no way that you can list them out, okay? So check that out. This has a restriction from 0 to 2 pi. Notice our last example here has no restrictions, okay? There's no restriction anywhere. See this? Okay. That's why you have to give me the formula. Okay. So cosine, it's going to be positive in here and here. So now you're going to give me the angle. Okay. There are 2 of them. Can you take a minute and tell me what this one is? What angle is that? Did you say pi over 6? Awesome. Okay. How about this one over here? Did you say 11 pi over 6? Great. Now, because there is no restriction, you can also say negative pi over 6. There's nothing wrong with give me one or the other. Again, because this is a regular trig function. So, how do you or how do us get an equation for all of them? So what we do is we're going to say, hey, how do I get back to this location every time? To get back to it, then you're adding a full revolution. And a full revolution is really 2 pi. But what if I want to add 2 full revolutions? Then you can use k. So say that where k is any integer, okay? Same thing with this, right? How do I get back to, for the purpose of demonstrating, let me erase this. You don't have to, just keep it where you have it at. Okay, so we decided to have it here, which we'd already had. Okay, then here. Now how do I get back to here every time? Well, same thing, right? I would add a full revolution. So whatever answer you write down here, you write 2 pi k. And if k is 0, then you have your first answer originally. Then if k is 1, then now you are adding 12 pi over 6. 12 pi over 6 reduces down to 2 pi. So that's why you're going to end up with the next answer in the next period, okay? So, and again, where k is an integer. So how do we write this? Theta is pi over 6 plus 2 pi k, and yes, you will need 2 different equations. And theta equals, I'm going to use just positive angles here, plus 2 pi k. Okay, and then I can just spell the k one time because they're both the same set of integers, okay? K is any integer. So this is my equations. And then it said, hey, give me 6 of them. So for me, when it says give me 6 of them, I'm going to say, hey, let's k be 0. When k is 0, then I have pi over 6 and 11 pi over 6, okay? How about when k is 1? When k is 1, then remember, 1 is really 2 pi times 1, which is 2 pi. But I need to add it to the denominator of 6. So the first thing I'm going to do is I'm going to convert that into 12 pi over 6. So now I'm just going to go, hey, what if I add 12 pi over 6 to this? So now I have 13 pi over 6. What if I add 12 pi over 6 to that? So now I have 23 pi over 6. So that's a total of 4. Then I'm going to keep on going when k is 2. So when k is 2, what I do is I'm just going to add 12 pi over 6 to these. So 12 plus 13 is 25 pi over 6. And then 12 plus 23 is now 35 pi over 6. So your 6 solutions are, theta is pi over 6, 11 pi over 6, 13 pi over 6, 23 pi over 6, 25 pi over 6, and 35 pi over 6, okay? Now, do I have to have all positive solutions? No, but most of us prefer positive numbers over negative. There's nothing wrong with negative numbers. I will also accept them, but your book, I think, most likely will have all positive answers, so we're just going to keep it consistent with the solutions in the book. Okay, are you ready for B? B, we are going to do the same thing. Are you ready? I don't have to do anything, so now I'm just going to compose both sides by sine inverse. So theta equals sine inverse of 1. Okay, now, but the original question is not an inverse, so I don't have restriction really, but there's only one location that sine is going to be positive, which is pi over 2. Okay, so it looks like I only need to have one equation. So 2 theta equals pi over 2, okay? And again, I'm just gonna go and add 2 pi k because that's what the period is for the regular parent function of sine. But if you see right here, there's this 2 in the front, so I'm gonna multiply each and every term by 2. Okay, so now I'm going to solve. Theta is pi over 4 plus pi k, and where k is, the symbol means contains in any integer. Okay, so z is the symbol for integer, so fancy way of writing it. That's the equation. Now I'm going to go and add a pi k to each. So pi is, if you think about it, your period for this equation is 2 pi divided by b, right? And b is 2, so that's why you have a period of pi, and that's how this is right here is related. So what you are doing is that in each period there's only one solution, versus in this question each period has 2 equations. That's why there are 2 each period has 2 answers. That's why there are 2 equations. Okay, so how do I get the 6 answers? I'm going to do the same thing. I'm going to let k be 0. So if k is 0, your first angle is pi over 4. If k is 1, 1 times pi is pi, but pi with the denominator of 4 is 4 pi, okay, over 4. So I'm going to add 4 pi over 4 every time. So the next one would be 5 pi over 4. When k is 2, then I'm going to add 4 pi over 4. 9 pi over 4, and k is 3. Keep on going, okay, so until you get 6. So I'm going to have, let's see, 4 plus 9 is 13 pi over 4, when k is 3, and no, 4. I'm going to add 4 to 13, so this is going to be 17 pi over 4. How many answers is that? 1, 2, 3, 4, 5, and then one more. When k is 5, I'm going to add 4 pi to that, so that's going to be 21 pi over 4. So here are your 6 solutions. Theta is pi over 4, 5 pi over 4, 9 pi over 4, 13 pi over 4, 17 pi over 4, 21 pi over 4. And box that up. All right. Okay, so let's see. We did 2 problems already. One was involving cosine, one was involving sine, and then now we're on the last one, which is tangent, okay? And if any time that you feel like this video is going too fast, rewind, okay? Pause. That's the beautiful thing about videos. Okay, last one. Let's do it. Tangent of theta divided by 2 equals 1. So similarly, I'm going to do composing tangent inverse, okay? So tangent, remember the original is normal trig, no restriction. Tangent is positive in 1 and 3, right? So the question is, hey, theta divided by 2 is what? What quadrant, what angle in quad 1 is going to give me tangent of what in quad 1 is 1? Did you say pi over 4? Yay! Okay. How about quad 3? Tangent of what in quad 3 is also 1? Did you say 5 pi over 4? Okay, I'll take it. Now, normally, I'm going to say that you would write 2 equations, okay? But here's the thing. You can, writing 2 equations like the first one is perfectly correct because I can't make it equal to 1 equation, okay? And what I mean by this is from one angle in quad 1, there is not an equal, let me get a different color, there is not an equal measurement, okay, on the left-hand side of it, and there's not an equal measurement on the right-hand side of it for me to get to one another without using both locations. But for this one, this angle, instead of adding 2 pi to get back to itself, what I can do is first erase, okay? What I can do is I'm going to add pi. Oops, I just erased. I'm going to, let me mark this back. I'm going to add half a circle to get to the second answer. Half a circle is pi. So it's easier, as you can see, to just add a pi. Why do I add a pi? Because pi is also the period for y equals tangent of x. So you can see I'm adding just pretty much the period for each of these equations, okay? So pi over 4 plus pi, because that's the period. And then we add k at the end because we will have to define what k is. But I still have to solve for theta by multiplying each and everything by 2, okay? So now theta is 2 pi divided by 4, reduce that to pi over 2, plus 2 pi k, where k is contained, this means contained or in, or belongs, and the integer. So that right there is 1 equation, okay? And you can only have 1 equation for tangent because the angles right directly across from one another are resulting in the same exact solution, okay? Only for tangent and cotangent. If you write 2 equations, I'm going to take points off because it's kind of like not reducing, so keep that in mind. Now let's write down our first 6 solutions. I'm going to let k be 0. If k is 0, then I'm going to have an angle at pi over 2. K is 1. then if you see this, I'm really adding a pi. I'm sorry, not a pi, 2 pi. And, oops, and 2 pi is like 4 pi over 2, right? Common, oops, I don't know, 2. Common denominator, okay? So if I add 4 pi over 2 to pi over 2, then now I have pi over 2. K is 2, add another 4 pi over 2, that's 9 pi over 2. K equals 3. That means theta is 4 plus 9 is 13 pi over 2. K equals 4. Add another 4 pi, so that's 17 pi over 2. K equals 5. Last one. And that's going to be 4 plus 17 is 21 pi over 2. So your first 6 angles are, let's write it down so we can box it up. Here we go. Ready? Pi over 2. 5 pi over 2. 9 pi over 2. 13 pi over 2. 17 pi over 2. 21 pi over 2, and voila. So those are the 6 solutions, and these over here are your equation. And yes, you do need to know how to write your equation. Okay, this is the end of our 7.3 notes. All right, y'all. So 7.4, trigonometric identities. In the box says, 2 functions f and g are said to be identically equal if f of x equals g of x for every value of x for which both functions are defined. Such an equation is referred to as an identity. Okay, so an identity is when they are, oops, I meant to highlight. An identity is when they are already equal. Okay, so, whoa, it's frozen. Give me 1 second. It's not responding. Come on, Microsoft Word. All right, there you go. So an identity is already, okay, an equation. That means they are equal to each other. So an equation that is not an identity is called a conditional equation. So we don't need to worry about conditional equation. We are going to be working with the identity. Now, chapter 6, which this is the review unit, unit 0 for you, or from last year. As we know already, tangent is always going to be sine divided by cosine. Cotangent is the reciprocal of that, so that's going to be cosine divided by sine. Cosecant is the reciprocal of sine. Secant is reciprocal of cosine, and cotangent, again, as mentioned, is reciprocal of tangent. So cotangent is the reciprocal of tangent. Now, these 3 right here are ultra important that you must memorize them by now if you didn't already from last year. So the first one was sine square. Let me write this out, and I'm gonna show you how to get the other 2 very quickly. Okay, so this is called the Pythagorean theorem for trig. If I take that one function, sine square plus cosine square equals 1, and divide each and every term by sine square, then that means I'm going to get 1 cosine square over sine square, as you know already. That's cotangent square of theta. And 1 over sine squared, that's a reciprocal function, so that's cosecant square. Oops, I'm missing a c. Cosecant square of theta. Now, that's how they came up with this right here. Mind you, you don't have to memorize a lot of things if you can just derive it yourself, okay? Now, what if I don't feel like dividing everything by sine square? Can I technically divide everything by cosine square? Sure. You're probably going to guess it, that it's going to give you the other identity that's sitting in that box. So divide everything by cosine square. There you go. Cosine square of theta, and cosine square of theta. So sine square over cosine square, as you know, that's going to give us tangent square of theta plus 1. That's a reciprocal function, so that's going to be secant square of theta. So that's going to give you right there. So if you can do the math quickly, you can get the other 2 Pythagorean theorem trig function pretty quickly. Now, we talked a little bit about odds and even identities, or odd and even functions, I should say, in unit 0, which is your review unit, okay? We talked about sine being an odd function. we talked about cosine being an even function. Tangent was an odd function. Cosecant is an odd function. Secant is an even function. And cotangent is an odd function. Okay, so as you can see, 4 are odds and 2 are even. And we talked about this a little bit too, and I'm just going to bring this up again. This is an even function because it's symmetric about the y-axis. This is a basic odd function, This is a basic odd function because it's symmetrical about the origin. So when I test it out, let's say I'm going to pick a positive value of x, it should equal to a negative value of x. So algebraically, we say, okay, f of negative x must be identical to f of positive x. So that's why you see all of the even functions, okay? As you can see here, this is even. All the even functions, which is this guy right here and this guy right here, when you have a negative angle, it's identical to a positive angle. Not so much on odd, right? So if this is an x, as you can see, this is negative x, and the outputs are not the same. But if I say f of negative x, which as you can see in this function, it should be -1 times f of positive x. Okay, what do I mean by that? So let's just use that function for a sake of simplicity. So what if x equals 2? Then if I'm testing this function right here, f of -2, which is really -2 to the 3rd power, which is -8. Obviously, it's not going to be the same as f of 2, because 2 to the 3rd is 8. But what if we go, okay, -1 times that? Okay, then now it's -8. So that's why this is true for all odd functions. So when it's an odd function for the degree, you can definitely, or the angle, then it's exactly the same as if we were to take -1 times the function of its positive angle, which is going to be super useful. So moving on here for the guidelines. Guidelines means, hey, these are just some hints. You don't have to follow it, but it's a good idea that you do. Guidelines for establishing identities. It is almost always preferable to start with the side containing the more complicated. Yep. Okay. Pick the side that looks scarier than the other. Now, rewrite sum or differences of quotients as a single quotient. What does that mean? If I have 1/2, take away 1/3, then they want you to rewrite it as single. That means over one common denominator. So find the common denominator and then match it up, okay? Sometimes writing one side in terms of sine and cosine functions will only help. So what that means is when you see tangent, cotangent, secant, cosecant, break it down in terms of sine and cosine, and not always, but it says sometimes. Always keep your goals in mind. As you manipulate one side of the expression, you must keep in mind the form of the expression on the other side. Now, don't lose track of what you are trying to prove, and do not, again, remember repeating, do not prove both sides at the same time, okay? Example 1, we will start the process of writing proofs with easy problems. A, simplify tangent of theta divided by secant of theta, and I'm giving you a hint here, by rewriting each trigonometric function in terms of sine and cosine. So in writing proofs, I always want you to write your steps down. And the reason is that some of you do your math horizontally, some of you do your math vertically, some of you just do it any space you have on your paper. So I can't really follow it. So if you number your steps, then at least I know where to go next. Now in here it says make sure you convert into sine and cosine. So tangent is going to be sine divided by cosine, okay? Then I'm going to write divided by this way, secant. Secant is the reciprocal of cosine, so there it is. Well, when you're dividing by fractions, you are going to change and flip, right? Change it to multiplication, flip it to cosine over 1. Then from here, we can definitely reduce. That allows us to to simplify to sine of theta, and we're done. Now, when you're done, so I know that you guys are done, can you just put your initial on it? Angie Bloom, Lewis, I don't know, Lewis Clark, right? Whatever your last name and your first name is, just put your initials on there so I know you're done instead of being stuck. B, show that sine of theta divided by 1 plus cosine of theta equals to 1 minus cosine of theta divided by sine by multiplying the numerator and denominator by 1 minus cosine of theta. So again, write the question down. Since it's already on my paper, I'm not going to, but your step number 1 should always be the side that you pick to prove. Yes, you can change your mind, then you just have to do it again and put the new number 1 down. Okay, so it's to give you a hint, it says multiply both sides by, both numerator and denominator by the conjugate, which is 1 minus cosine of theta. 1 minus cosine of theta. Then step number 2, on the denominator, the conjugates, meaning that I don't really need to FOIL that out. I'm just going to multiply the first 2 terms and the last 2 terms. Okay. Now, if you don't remember why we don't really need to FOIL, then you can FOIL it right now. So here we go. If 1 times 1 is 1, 1 times minus cosine is negative cosine, cosine times 1 is positive cosine, and then this one gives us a minus cosine square. So you can see when they're conjugates of each other, the middle 2 terms will always cancel out. Now on the numerator, I can technically distribute it, or I can leave it for now. It's up to us to decide. Then step number 3, as you can see, by the way, no, you may not cancel this and cancel that, and thinking that in the bottom it's just now 1 minus cosine left. That would be ultra illegal. Okay, so cancel, don't do that. That's a big no, no, no. Now, keep in mind what we're trying to get to. We are trying to get to 1 minus cosine on the top. So obviously, I want to keep 1 minus cosine on the top. I'm not going to try to get rid of it. But your identity says cosine square of theta plus sine square of theta always equals to 1. So what if I manipulate this and move, right? Move things around, such as move cosine over here. So sine square of theta equals 1 minus cosine square of theta. That allows me to substitute in the denominator to be sine square. So now just copy the numerator. Now we can cancel. There's 1 of that on the top, 2 of that on the bottom. I should have 1 left, right? So as you can see, my last step is to write the ending, which is 1 minus cosine of theta all over sine of theta. That matches the right side, and I'm going to write my initial, and I'm done with that proof. Now, what if I decided to pick the right side? Because for this particular question, both left or right are as equal difficulty level. So that means I'm trying to get this to look exactly like the left. Well, then that means I'm going to multiply the conjugate of the numerator. Okay. As you can see, these are hints that you can use. Then step number 2, do I have space to go vertical? Let me check. It's frozen for me again. Okay, I don't have enough space for vertical, so I'm just going to horizontal. So on the denominator, I will now leave the sine of theta times 1 plus cosine of theta. On the top, those 2 are conjugates. So as we spoke about this earlier, you only need to multiply the first 2 terms and the last 2 terms. Now, step number 3, this is an identity, right? Just like that, except that you can move things around to create new different identities. So that I can take it out and substitute with sine square of theta. That will allow me, as you can see, oops, I forgot parentheses right there, to reduce. Okay, so by reduction, there's 1 left on the top. So last step, I'm going to write number 4, sine of theta all over 1 plus cosine of theta. Let's check to see if that's where that's what the left side is, and it is. And write initial to tell me that you are done with your proof instead of I'm stuck. Let's see, how many more do we have left? Example 1, that is. I got 1C and 1D. Okay, just 2 more on example 1. 1C, simplify by rewriting the expression over a common denominator. Now this is the guidelines or the hint on number 2, if it's allowing you to see it at all once it's done freezing. Okay. Number 2 says rewrite sums or differences of quotient as a single quotient. So that's really what this is doing. So step number 1, copy down the problem again. 1 minus sine of u plus 1 over 1 plus sine of u. Your common denominator, you don't have a lot of choices here, so that both, you're just going to have to multiply those two together. So 1 minus sine of u. And again, you have to show me all of your steps. No, you can't do proofs in your head. The whole reason of doing proofs is that I'm trying to understand your head. I'm trying to get in your head. Okay. So as you can see, the first fractions I multiply by 1 plus sine of u. So what I multiply to the bottom, I will now multiply to the top. Now the second fraction I multiply by 1 minus sine of u. So that's what I am doing. So number 3, we now have a common denominator, so we can put the numerator together. 1 minus and 1 plus. Okay, sine of u. On the top, I have 1 plus sine of u plus 1 minus sine of u. From here, we can see if we can simplify a little bit. Bam and bam. Okay, so that allows me to say, oh, wait, that's really 2. Oh, this is step number 4. Step number 4. On the denominator, I'm going to distribute those, and they happen to be conjugate. So it's 1 minus sine square of u. Step number 5, by now, 1 minus sine square of u is really cosine square of u. 2 divided by that. Step number 6, I'm out of space, maybe not. Step number 6, I'm going to go further. If you can, try to go all the way until you cannot have fractions anymore. So that's really 2 times 1 over cosine square of u. Step number 7, that's really 2 times 1 over cosine's reciprocal of secant square. And that is as simple as you can go. Initial, yeah, that means it's a success. Okay, last example last problem in example 1. Simplify by factoring. Yeah, I love factoring. So step number 1, copy the question down. 1 minus cosine square of v all over sine of v plus cosine of v times sine of v. Okay. Step number 2, on the numerator, it's a difference of 2 squares. So you can go 1 minus cosine of v, 1 plus cosine of v. Remember back in the day, it's like x squared minus y squared, or I can say x squared minus 9, and then you go, ooh, x plus 3 times x minus 3, same thing, right? So algebraically, that's, oops, I meant 3 again, this is y. Well, it's frozen again, there you go. Like that. So same thing, when you see Trig and the factoring rules are exactly the same still. On the denominator, they both have sine in common, so take out your sine of v. Then we have 1 plus cosine of v left. As you can see, those two factors are identical, so we can cancel. Next, we have 1 minus cosine of v divided by sine. We can go about this a couple different ways. Let me split it up to see if that's any simpler. What if I go, step number 4, that is. What if I go 1 over sine, oops, I forgot v. Sine v, take away cosine v over sine v. Okay, and then step number 5, 1 over sine of v is going to be cosecant of v. Take away cosine divided by sine is going to be cotangent of v. So I think non-fraction format's probably a little bit better. So I'll go all the way to number 5. And yeah, that's example 1, just kind of basic hints. Until I see you next time.